Okay, class, welcome back. This is video 3 on dealing with chemical reactions and chemical equations. Our last video, we talked about predicting products formed in chemical equations. In this video, we're going to talk about how we observe the law of conservation of mass within a chemical reaction and how we illustrate that. Our goal for today, or our objective for today, is that we will be able to balance chemical equations. So in saying all that, let's dive into our material. The law of conservation of mass says that mass cannot be created or destroyed within a chemical reaction. For example, in the synthesis of water equation, we would use 2H2 plus O2 yields 2H2O. Notice the elements in which we used in the product side are the same elements, individual elements we use in the reactant side. We don't have some like random nitrogen or something like that come up. We only had hydrogen, oxygen in the reactant side. So our product is only going to contain hydrogen and oxygen. We do not create an element. We do not destroy anything. Nothing is omitted. Okay? We instead used what we had and created a compound. In other words, the elements you start with in the reactant must be present in the product in some form or fashion. Another part of the law of conservation of mass is that the quantity of each individual element must be present within equal parts on each side of the equation. So I must have the same amount of hydrogen on the reactant side as I do in the product side. Or I might need all the same amount of oxygen in the reactant side and the product side. For example, in this equation, the synthesis of water, we have 2 oxygen atoms on the reactant side. Then I must have 2 oxygen atoms on the product side to observe the law of conservation of mass. When we are counting atoms or counting elements in general, we are presented with a chemical equation, whether that's a single element like N2 or Na, or a formula or compound like H2O. Okay? In order to be able to count these atoms, we need to understand how to read these formulas. Let's look back at our synthesis of water equation, and we see that there is a subscript after both the hydrogen and oxygen on our reactant side. This tells us how many of each element we start out with. So there's H2 plus O2. That means that we have 2 hydrogens and 2 oxygens that we start out with. An important thing to understand, though, in this case, though we have subscripts for both H2 and O2, we might not have a subscript for some elements. And if that's the case, there is an understood one of that element. So if I just had lithium, Li, and there's no subscript with it, then there's understood that there's only one lithium atom. The next number we want to talk about and see in our equation is that there's a big coefficient in front of our elements or our compounds. What does this coefficient mean? Well, this coefficient says that there are, whatever that number is, X amount of copies of whatever is behind it. Our hydrogen has a subscript of 2, so there's 2 of them. And we have 2 sets of those, so 2 times 2 is 4. Our oxygen has a subscript of 2 with nothing in front of it, so we're going to assume that's 1. Okay, so 1 times 2 is 2, so we have 4 hydrogens and 2 oxygens. Now we go to our product side. Let's see if that matches up. Then we got 2 H2O, so 2 times H2, so H2 is 2 hydrogens, and we have 2 of them, so that's 4 hydrogens, so 2 times 2. And O, there's no subscript, so we're going to take this 2 coefficient, apply it to that O at the back, and we get 2 times 1, because there's no subscript, we assume that's a 1. That's going to give us 2 oxygens. So we have 2 oxygens, 4 hydrogens on the product side, and 2 oxygens, 4 hydrogens on the reactant side. So that means we are balanced out. Let's go a little bit more in depth with this, though. Now that we understand coefficient subscripts, we can talk about the law of conservation of mass in chemical equations. In a chemical equation, we can add coefficients in front of elements or compounds. This will then change the amount of that element or every element within that compound. Our goal for balancing equations out is that we are able to observe the law of conservation of mass. In other words, the amount of elements we have in our product, each element, the amount of them we have of them, is going to equal that same amount of elements on the product side. So in our synthesis of water, the hydrogen and the oxygens on the reactant side, we had the same number of them as we did on the products. So let's take a look at another equation. Let's work this out and balance it out from the beginning. Okay, let's look at the synthesis of potassium iodide. Okay, because it's a synthesis reaction, we know that it's two individual elements coming together to form a compound. So we got potassium plus iodine, so K plus I2 is going to yield potassium iodide, which is Ki. Okay, to start out, let's see how many of each element are on both sides of the equation. So first I'm going to come across my potassium atom and I write down K. I see that there's no subscript or no coefficient, so there's only one potassium atom on my reactant side. Okay, good. Now we go to my iodine. Iodine has a subscript of 2, so no coefficient, subscript of 2. 2 times 1 is 2. So I have 2 iodines and 1 potassium on my reactant side. Let's go to my product side. I have Ki. I write down my K first. There's no coefficient in front of it, and there's no subscript right behind it, so there's only 1 potassium. Okay, so good so far. Potassium's lined up. We have 1 on the reactant side, 1 on the product side. Now let's go to our iodine. Again, no coefficient in front of our potassium iodide, and there's no subscript after the iodine, so there's only 1 iodine. This is where we run into the issue, because we have two iodine atoms on the reactant side and 1 on the product side. That means the law of conservation of mass is not observed, so this is not a balanced equation. So we got to change it up to fix it. Okay, well, the easy thing to do is, well, I need 2 iodines, so I'm going to multiply everything with my iodine by 2. So I need to put a coefficient in front of my potassium iodide on my product side. By doing that, I now change my formula for iodine. Instead of 1 times 1, it's going to be 1 times 2, and that gives me 2. So now my iodine matches up 2 iodine in the product, 2 iodine in the reactant. But the issue is if I put 2 as the coefficient in front of the potassium iodide, that means the 2 also applies to the potassium. So now, instead of just having 1 potassium on the product side, I have 2 potassiums on the product side. So now this is not balanced out again. We have 1 potassium on the reactant side and 2 on the product side, 2 iodine on the reactant side, 2 on the product side. Well, now I got to go to my reactant side and balance that out. I want to have 2 potassiums. I want to be able to do that, so I'm going to have to add a coefficient of 2 in front of my potassium atom. Now all I do is, instead of 1 times 1, it's going to be 1 times 2, and that gives me 2 potassium atoms. So this now is balanced out. We have, check everything through, we have 2 potassium atoms on both sides, we have 2 iodine atoms on both sides, so it's balanced out. So our balanced equation for the synthesis of potassium iodide would be 2 potassium plus iodine yields 2 potassium iodide, or 2K plus I2 yields 2Ki. Okay, so let's work another one now. Now let's do a single replacement reaction, where this time we're going to use our compound of potassium iodide and mix it with phosphorus. Okay, so if it's a single replacement, we know we have a compound, potassium iodide, and a single element, phosphorus. So it's going to be Ki plus P. Now, what is that going to yield? Well, my single element is going to replace my iodine. So we're going to have Kp plus I2. Iodine is what we call diatomic, so it's always found in sets of 2. So that's how come we have I subscript 2. Our potassium and phosphorus still need our oxidation numbers. Potassium has oxidation of a +1, phosphorus has a -3. We cross those, and now we get the full compound of K3P. So our chemical formula, or our base formula, should read Ki plus P yields K3P plus I2. Now we can start balancing. Okay, so I write down each element I have. So each side I have a potassium, an iodine, and a phosphorus. So I'm going to write that down on both sides. Now let's count how many we have. Well, on our reactant side, our potassium iodide, we only have 1 potassium atom. It doesn't have a subscript. It doesn't have a coefficient, so there's only 1 of them. We have 1 iodine atom, same concept, no coefficient, no subscript. And we have 1 phosphorus atom. no subscript, no coefficient. So everything should be 1 on my reactant side. Let's look at my product side. This is where we start getting some differentiation. So I have a subscript with my potassium of 3. So I have 3 potassium atoms on my product side. Phosphorus does not have a subscript, so I only have 1 to start with. And I2, iodine, has 2 iodine atoms. So we look at our initial setup. We have one potassium on the reactant side and 3 on the product side. We have 1 iodine on the reactant side and 2 on the product side. We have 1 phosphorus on the reactant side and 1 phosphorus on the product side. So we need to start balancing this out. Our reactant product side are not the same. First thing we're going to do is try to account for our phosphoruses on the product side. Okay, I'm going to do this by putting a 2 in front of the 2K3P. Okay, I do that. That changes my phosphorus from 1, because there's a coefficient in front of it now of 2, to 2. Still no subscript, so 1 times 2 is 2. This is due to the coefficient. But because this is a compound, my potassium is also affected. So now I have 2K3. Okay, that means now 2 times 3, I now have 6 potassium atoms. So right now we have 6 potassium atoms and 2 phosphorus atoms on our product side. Well, now we got to go fix our reactant side. Let's do it for potassium now. So I'm trying to get 6 potassium atoms on my reactant side. All I do to do that is, since I only have 1 potassium atom on the reactant side, is I put a 6 as the coefficient for my potassium iodide. In doing that, now it changes everything up. It changes now in the reactant side. I have 6 potassiums, 6 iodine, and 2 phosphorus. While on my reactant side, now I have 6 potassiums, 2 iodines, and 2 phosphoruses. So the only thing we don't have balanced out now is our iodine. So now we got to go in and get our iodines. On our reactant side, we have 6. On our product side, we only have 2. Well, I2, how to get that to 6, all we're going to do is put a coefficient of 3, because 3 times 2 is going to give us 6. Okay, once I do that, that brings my I2, or my iodine in my product side, up to 6. Now we have 6 potassiums on both sides, 6 iodines on both sides, and 2 phosphoruses on both sides. Okay, so now that gives us a balanced equation of 6Ki plus 2P yields 2K3P plus 3I2. Okay, last equation. Let's do a double replacement one now. Let's do carbon dioxide plus nitrogen, or dinitrogen trisulfide. Okay, so if we switch out our sulfur and oxygen portions, then we get carbon disulfide plus dinitrogen trioxide. In other words, we get CO2 plus N2S3 yields 3CS2 plus N2O3. Okay, this is going to be a lot, so here we go. Let's do our reactant side first. We have carbon, oxygen, nitrogen, and sulfur. Okay, so we got 4 elements. Now we got to figure out how many we have as our base part. There is no coefficient and there is no subscript for carbon. So we only have 1 carbon to start with. Then our oxygen has a subscript of 2, but still no coefficient, so we only have 2 oxygens to start with. Our nitrogen has a subscript of 2, but no coefficient, so 2 to start for there. And our sulfur has a subscript of 3, but no coefficient, so we have 3 to start there. So to start out, we have on our reactant side 1 carbon, 2 nitrogens, 2 oxygens, 3 sulfurs. Now let's do our product side. So we have carbon, oxygen, nitrogen, and sulfur. Okay, we have still 1 carbon, no coefficient, no subscript. Our oxygen, now if we go all the way over to the N2O3, we have 3 oxygens because it has a subscript of 3. Then our nitrogen has a subscript of 2, no coefficient, so we have 2 nitrogens. And then our sulfur has a subscript of 2, but no coefficient, so there's 2 of those. So on our product side, we should have 1 carbon, 3 oxygens, 2 nitrogens, 2 sulfurs. So we see our sulfurs and oxygens are a little messed up right now. Okay, so let's go with our oxygen on our product side first. If we look on our product side, we have 3 oxygens to start with, and we're needing to get 2 oxygens on our reactant side. Well, I can't decrease anything, so I got to find something that they both have in common. Usually the best idea is to use a coefficient of how much the other has. So in this particular instance, I have 3 oxygens on my reactant or product side and 2 oxygens on my reactant side. I'm going to use a 2 on my product side as the coefficient in front of N2O3 and a 3 on my reactant side in front of CO2. So let's write those out real quick. If I use the 2 on my product side, that now brings my oxygen up to 2 times 3, so 2 the coefficient, 3 the subscript. That's 6 oxygens. And then my nitrogen now is affected because I put a coefficient in front of everything. So I had 2 nitrogens, now I've got 2 times 2, then I have 4 nitrogens. Okay, so now I have 1 carbon, 6 oxygens, 4 nitrogens, and 2 sulfurs on my product side. We put a 3 on the CO2, that gives me 3 carbon atoms. Our oxygen had 2 subscript, and we put a 3 as coefficient, so that gives me 6 oxygen atoms. So our oxygens are matching up now. But the thing is, we still don't have our nitrogens, sulfurs, or carbons adding up now. So now I'm going to go back to my product side. I need 3 carbons, so I'm going to put a 3 in front of my carbon disulfide, or CS2. If I do that, now that brings my carbons, I had no subscript with my carbon and 3 is a coefficient, that brings my carbon up to 3 total carbons. My sulfur had 2 as a subscript and 3 is a coefficient, so that's going to give me 6 sulfurs. So now on the product side I have 3 carbons, 6 oxygens, 4 nitrogens, and 6 sulfurs. Okay, so this time now I have on my reactant side 3 carbons, 6 oxygens, 2 nitrogens, and 3 sulfurs. Okay, I want to be able to get my nitrogen sulfurs to match the product side. So to do that, I'm going to put a 2 as a coefficient in front of my nitrogen dinitrogen trisulfide. In doing that, I now have 4 nitrogen atoms, so 2 is a coefficient, 2 is a subscript, that's 4, and 6 sulfur atoms, 2 is a coefficient, 3 is a subscript, and that's going to be 6 total sulfur atoms. Now, if I'm not mistaken, everything should be balanced out. We should have 3 carbon atoms on both sides, 6 oxygen atoms on both sides, 4 nitrogen atoms on both sides, and 6 sulfur atoms on both sides. So that gives me a balanced equation of 3 CO2 plus 2 N2S3 yields 3 CS2 plus 2 N2O3. Okay, so that's enough to throw at you this time. I just want you to understand that with balancing equations, there's going to be a lot of plugging and playing and trying to make sure everything kind of works out. I just say take it one element at a time. Don't be afraid to erase stuff, and don't be afraid to retry different numbers. Okay? And saying all that, this was probably a really long video for y'all, so thanks for sticking with me, and keep up the good work in class. See you next time.